Welcome, class. We're going to begin chapter 10. And this chapter is maybe one of the more challenging chapters you're going to have in this midterm portion of the stats class. To help you understand where we're coming from, I'm going to go with an intro problem here. Imagine that there are two sections of Spanish 101 taught this semester. We have noticed a mean language placement scores by the two sections are slightly different. The first section is taught by Professor Great and is primarily used a connection to Spanish grammar, while the other section is also taught by Professor Great, primarily taught from a speaking connection. So two different philosophies of teaching. At the end of the semester, each student takes the same placement test. The mean score for the first section, that would be the grammar section, 30 students is 225, standard deviation of 40. While the second section, that would be connected to speaking, of 36 students is 240 with a standard deviation of 50. Here's the question. Does this give evidence that is statistically significant that the philosophy used in the second section is superior to the first section? Well, why are we considering that? Well, the answer to that is this. The second section had a mean of 240. The first section had a mean of 225. This is a higher mean. The question is, does that indicate that learning the language connected to speaking is more effective than connecting it to grammar? That's what the test would be about. This is an example of what we consider testing between two populations. A population that is teaching with connection to grammar versus a population teaching with connection to speaking. Two different populations. Is one better than the other? In this case, was the second superior to the first? Well, there's a lot of variables that enter in here, which is why this is very difficult to do. And it's also difficult to show that there's a difference that would be statistically significant. The reason being that it's different is there's so many variables. For example, I could have two different professors teaching. One professor teaching grammar, but a totally different professor teaching speaking. Now, I eliminated that one in this example because I made them both the same professor. But that would be one variable that you would want to look at if you were running this study. A second variable that's going to be highly significant would be, does it happen to be that the second section has just more intelligent students in it? Historically, it's been well documented that the more intelligent students are, the easier it is for them to pick up another language. So the natural intelligence of the two sections is another very important variable that could disguise or skew the results of this test. And finally, a third variable here that would be highly significant would be, is there a greater number of students in this second section that have Spanish as their primary language? That would indicate that they would likely pick up that test and do better on that test because it's their first language. So all of those are variables that would have to be addressed if you're running this type of test. All that said, is this chapter, chapter 10.1, chapter 10.2, chapter 10.3, 4, is going to focus on running tests between two populations, So keep that in your mind first. So when I'm comparing two populations, obviously I have to have independent samples. I don't intentionally match up any type of samples. I'm taking them random samples that are independent. We can find confidence intervals between two populations, and we can also run hypothesis testing between two populations. We can do it for large samples, which would mean we're using, again, like we have in the past, z-scores. But I could also use it for small samples. And like we did in the past, that would indicate that we're going to use t-scores. So that's not that much new. Large sample z statistics, small sample t. Here's the part. Take a very close look at this. Super important. When I'm comparing two population means, we test the difference between them. Notice it's the difference, a subtraction symbol right there. The mean from population 1 minus the mean from population 2. Try to keep that in the back of your mind all the time during this chapter. We're testing the difference, testing the difference. I'm going to try to emphasize that throughout our lesson today. We're starting off today by looking at the difference between two population means. First of all, we're looking at a large sample, and we're going to look at confidence intervals. Notice it's for the difference between the two. Okay? So here's our formula. Confidence interval. Because it's two populations, it's the difference of the sample mean of the first minus the sample mean of the second. Because it's a large sample, I have a z-score. And my adjusted standard deviation looks like this over here. First of all, I would like you to recall a confidence interval, large sample, for a single population. For a single population, I just need you to compare these two now. Well, for a single population, I didn't compare a difference. It was just X bar. Plus or minus, if it was a large sample, I had a z-score. We took our alpha, divided it by 2, and we had our adjusted standard deviation, which you remember was S over the square root of n. That was for a single population mean. We did that in the last couple of chapters. Compare that to a two population mean, like we have the one here for two population. Now I'd like you to notice something. This adjusted standard deviation, I'm going to copy that down right over here. It was S over the square root of n. That's what that one was. Well, notice that could have been equal to the square root, and I could have taken the S and left it squared in there over n. Notice how that second expression, which is equal to the first, which we used for a single population, notice how this second expression compares to this. This really is the same as S1 squared over N1 plus S2 squared over N2. It follows and compares well with our single population confidence interval. For most of you, you're going to take this expression right here, and that's the expression you're going to use for that radical over there. So to make sure we have that down, I would expect that you would be able to say, my confidence interval is going to be X1 sample mean minus the sample mean from the second sample, plus or minus our z-score, alpha over 2. And now I'm going to put this expression in here. So it's going to be the square root of S1 squared over N1 plus S2 squared over N2. That's my formula for a large sample confidence interval for two populations. So make sure that you have that copied down. Large sample confidence interval for two populations. It should look like this. Obviously, the formulas get messier. And I'm afraid to tell you that's only the beginning of our lesson today as far as messy formulas go. There is some good news coming at the end, but the formulas get to be messy. What would you know, or what would you not know, about the mean of population 1 compared to the mean of population 2? Remember again, we test the population mean from one population to a second population, and we test the difference. So now, here's our confidence interval. I made up a confidence interval. I kept the numbers very simple first because I wanted you to understand what I'm trying to get across in this particular slide, okay? If the difference is somewhere between a -3 and a -1, what does that mean? What would I know or what would I not know about the populations if this is the confidence interval? The key that I need you to recognize is that this interval is entirely negative. Anything between a -3 and a -1 is a negative number. So we would be, whatever the confidence level is, if it's 95%, we would say we're 95% certain that the difference is between a -3 and a -1. Well, what does that mean in reference to the population? Well, for you to get a difference that's negative, the only way that can happen would be if the first number is smaller and the second number is larger. A smaller minus a larger would equal a negative number. So in this example, if the interval is entirely negative, that means that the second population must have a larger average than the first population. The second population must have a larger mean compared to the first population. When it's entirely negative, the second one must be larger. We would be 95% sure of that, or whatever the confidence level. What happens, and I'm going to put a confidence level in here, 95%. I'm just making that up now. So if I have a 95% here, but notice this time it goes from a negative number all the way up to a positive number. Again, what do we know then, or what do we not know? Well, if it's negative, the second population had to have a larger mean. But if it's positive, the second population had to have a smaller mean. Because if the first one was the larger, and I subtracted the second one, and that was a smaller mean, then I would end up with a positive difference. So because this could have been a negative difference, which would mean the second one is larger, or the difference could have been positive, which would mean the first one is larger, we would not know anything about it. We would be uncertain. We would not be able to be sure that one average is greater than another, either way. Finally, if I have a 95% confidence interval, and it goes from a +3 to a +5, entirely positive, that means that it falls entirely in this second setting, which means the first population had to be larger, because a larger number minus a smaller number will always give you a positive. So, in conclusion, if the entire interval is negative, you're 95% sure that the second mean is bigger. The third one here, if the entire interval is positive, you're 95% sure that the first mean is larger. If you got a negative and a positive, you really are not sure which one is greater. You'd have to be saying, I have no reason to doubt that they're still equal. When I'm looking at hypothesis tests, again, things get a little messier. If I'm looking at a large sample, but it's a single-tailed test, my alternative will either be a less than or my alternative will be a greater than. That's not new. But previously, we always just had one mu here. Now we're looking at a difference. If it's two-tailed, the null is equal. The alternative is unequal. That's like we've had in the past. But again, notice it's a difference is equal or a difference is unequal. The test statistic, z, in the past we just had x bar minus mu. Now it's the difference of the two samples minus the hypothesized difference. That would be this number here. We'll do a bunch of examples for that. Divided by the adjusted standard deviation, which is what this is about. So that means most of the time, our z, and copy this z down now, it's going to be this x1 bar minus the x2 bar minus the hypothesized difference from the null. That comes from this number right up here. All divided by, rather than this one, usually we end up having to go with the sample standard deviations. So this turns out to be S1 squared over N1 plus S sub 2 squared over N2. That's just that adjusted standard deviation in place of this one. But again, make sure that you have that formula down. That's S sub 1 squared over N sub 1, S sub 2 squared over N sub 2. We add each of those fractions and then take their square root for that denominator. This is kind of a duh, but some required conditions. They got to be independent samples. However, whatever I happen to choose from population 1 does not affect how I choose population 2. They're independent. And for it to be a large sample, both samples must be 30 for that central limit theorem to kick in. I'm going to now do a test here once. So go ahead and read this problem. To make for some more room, I'm going to tear part of this top off because I'm going to need the room. So bear with me a minute. I should have done this earlier. I apologize for that. Well, let's grind through this once. First of all, the hypothesis test. They're asking, does it give strong evidence? That's implying, of course, strong evidence is implying alpha is 0.05. Now, we're going to grind through once this entire problem and see how we've put it out. The first thing we have to do, and this is super important for single-tailed tests, but we do it all the time, is we identify what population each one is about, okay? In other words, I'm going to let mu sub 1 equal something, and I'm going to let mu sub 2 equal something. Each of them in this case is going to be the mean, and we need to identify what population I'm referring to. So it's standard procedure to let mu sub 1 equal the mean of the first one given. Well, the first one given, first section was the grammar one. So it's the mean of the grammar, in this case, philosophy. The second one is when they taught the class connected to speaking. So it would be the mean of the speaking. I need to identify which one each is. So that's something that's new that you haven't had in the past. Previously, we just had a single mean of a single population. There was no doubt what was happening. So now, here we go with my test. I need to list the null, and I need to list the alternative. Look at what we're testing once. I'm testing is the second section superior to the first? Is this second one better than the first? This is one of the more challenging parts. I always list mu1 minus mu2, mu1 minus mu2, but now I have to be very, very careful getting this alternative. I'm looking to see if there's evidence that would show the second one is superior. Well, if the second one is superior, that means their difference would be negative, because if the second one is superior, it's a larger number than the first. That would mean that the score would have to be less than 0. I'm going to say that again. If the second section is superior to the first, that means the second average would be greater than the first. So if the second one is greater, when you take their difference, you get a negative number. That's my alternative. My null was going to be the opposite. We could either list greater than, or we can just assume that they're the same. I'm going to put equals. I could have put greater than, or I could have just put equals, but this one is the key, the alternative. Super important that you get that one in. You take your time putting that one together. Okay, step number 2. I'm going to list my alpha level. They didn't give me one, so the fallback, the default is alpha equals 0.05. My sample size, I had 30 and 36. So N1 was 30, N2 was 36. Both of them are 30 or more, so I'm going to be using a Z statistic. It didn't tell me specifically which type of test I had to run, whether it was a critical value or whether it was a p-value test. I'm going to choose to go critical value here. So I have a single-tailed test. Again, you don't need this drawing on the side. But I'm looking to show that it's negative. That would be this way. I need a line in the sand again. This is going to be my rejection region over here. Because it's single-tailed, all 5% is in that tail, which means I got 0.45 here. If you check that out, that means that this will be a negative 1.645 z-score. If I go over that, I'm in the rejection region. So my rejection region is Z is over that number, it's less than a negative 1.645. Again, you don't need this little drawing here, but it oftentimes helps you understand what's happening just a little bit easier. Step number 3, our Z formula. It's a long formula, x1 bar minus x2 bar minus the hypothesized difference. In most cases, that's going to be a 0, but it's this number, whatever it is up there, divided by the square root of S sub 1 squared, that's the standard deviation of population 1 squared over n sub 1, plus S sub 2 squared over n sub 2. This is the standard deviation from population 2 squared. So putting those numbers in, I won't do this every time, but I'm going to do it here for the first one. The mean of the first section was 225. That's my x sub 1 bar. So that's going to be 225 minus the mean of the second sample. Well, the second section is 240 is the mean, minus my hypothesized difference, which is 0. And I have that over the square root of my first standard deviation. Standard deviation for the first one was 40. So I would have to take 40 and square it. The sample size was 30. Plus the second standard deviation, which happened to be 50. Over that sample size, which was 36. You would need to take 40 square it divided by 30. If you put that answer down, unless you're really good with your parentheses, take 50 squared divided by 36, put those down, take those two answers, add them together, and take their square root. If you do that, you'll end up with a negative 15 all over 11.0805. Make sure you can go from your calculator here to get those numbers, and that gives you a negative 1.35. Well, that is not in the rejection region. 1.35 is about right over here someplace. It did not go over our line in the sand. It did not get into the rejection region. So that means, like we've had in the past, Z equal to a negative 1.35 is insufficient evidence to reject our null, and thus we continue to assume. What are we going to assume? The null. We continue to assume the null, which in this case means the mean between the two sections does not have a difference. We continue to assume there is no difference teaching connected to grammar versus speaking. I just had to write this conclusion in context of the problem. What are some key parts that are different here? Well, I had to define this. If you leave that out, you lose some points. Notice that you have the difference in both of those. That's a new part. Most of this is still the same. Rejection regions are found the same way. Your formula for Z is quite a bit more complicated. That takes some extra work. The conclusion is basically the same that we've been doing. Okay? I'd like to find a 95% confidence interval for that. And again, showing you one example there. Confidence interval. It's going to be the difference between the two means. You've seen this formula, you already have it written down. Plus or minus our z-score multiplied times square root, here's that same adjusted standard deviation we've been working with. That's the exact same as our denominator was for our z formula. So in our case, when I put these in, the first mean, you recall, was 225. The second mean was 240. Plus or minus our z-score. The z-score was like that rejection region. So that z-score in this one turns out to be, you gotta find it here. Maybe I don't have it listed. In this case, it's a confidence interval, so it is a little different because I'm taking the alpha and I'm putting it on both tails for a confidence interval. That means I have 2.5 and 2.5. That means I have a negative 1.96, a positive 1.96. So my z-score is plus or minus 1.96. This is the same substitution that we did for that z formula. So it was 40 squared over 30, and it was 50 squared over 36. When you evaluate that all out, your confidence interval turns out to be a negative 36.718 up to a positive 6.718. Notice it went from a negative to a positive. Because the difference could be negative, the difference could be positive, we're not sure which one's larger. So this again ratifies our decision of what we had with our hypothesis test. It's saying the same thing. We're not sure which one's greater. I'm going to be going a little bit faster now in this next example. I'll let you read through that. I apologize again. I should have tore this off. So let me do that a moment first. Right there, and tear this. Not a great tear, but I hope that it's going to work yet. Go ahead and read through that problem once first. It's concerned is the word that got partly tore off. Couple of things I'd like you to notice. Sample 50, both large. Both large because they're both greater than 30. They're asking for strong evidence, which means they're asking for an alpha at 0.05. And finally, they're asking, is there strong evidence to indicate, in this case, any difference? Any difference is screaming at us, two-tailed test. Two-tailed is where the null is equal, the alternative is unequal. As I had to do in the past, the first thing I need to do is to define what mu sub 1 is and mu sub 2. Both are means or averages of something. And we normally list them to how they were listed first in the problem. The first one listed was the mid-September mean. So this is the mean of September. November, you can no longer park on the street, so they have to use a parking lot. So that would be the mean of November for the second one. I had to list that to identify which one is which. Next, I'm going to list my null and alternative. My null, my alternative. Both of them are a difference. This one is much easier than the first one because it is asking, is there any difference? That's screaming at us, two-tailed test. Two-tailed always means the null is equal, the alternative is unequal. We say 0 because we're looking at if there's a difference, positive difference or a negative. The null is a 0. Step number 2. Strong evidence indicated alpha was 0.05. Both my samples were 50. So I'm going to list it this way. N1 equals N2. Both of them equal 50. I could have listed them separately. N1 equals 50, N2 equals 50. But either way, I'm going to have a Z statistic. Last time I ran a critical value test, it didn't specify here. So this time I'm going to run a p-value test. I'm going to go right to my Z formula. Z formula was sample mean of the first population minus the sample mean of the second population minus our hypothesized difference, that number there, all divided by, in this case, the adjusted standard deviation. That means that I'm going to have the standard deviation of the first population over the sample size, plus the standard deviation of the second population over the sample size. And now I need to substitute all of those in. So my first mean was 4.82. My second mean is 5.18. That's the difference minus our hypothesized difference, which is this number, usually 0, divided by the square root of our first standard deviation, which was 1.47 squared, over the sample size, which was 50, plus the second standard deviation, which was 2.31 squared over that sample size, 50. Gets to be kind of messy. I get that totally, but you have to be able to grind it out. Turns out to be a negative 0.93. I'm going to find the p-value just as I did back in chapter 9. So this one, my p-value is going to be, because it's two-tailed, it's going to be 2 times 0.5. If you check up the 0.93, it turns out to be closest to 3238. just in case you didn't see that, let's just see if we can find that a moment. 0.93, here's 0.9, there's 3. That's where that 3238 came from. We have to double that difference. So that's why the p-value turns out to be 0.35. It is not less than my alpha. So it means I have insufficient evidence. So P equal to 0.35 is insufficient evidence to reject our null, and thus we continue to assume our null, which means the difference was 0. We continue to assume there is no difference in the mean, the average that is, the mean time to park in September compared to November. And that would be my test. We'd like to find a 95% confidence interval as well. If you don't mind, I'm going to do that right over here on the side. That formula for the confidence interval, you recall, was x1 bar minus x2 bar plus or minus our z-score times our adjusted standard deviation. That's the same as this denominator over here. So that's going to give me that s sub 1 squared over n1 plus s sub 2 squared over n sub 2. So I have the same difference that I had right over here, 4.82 minus 5.18 minus my z-score, 95% in this case split in two tails is the same 1.96 that we've been using. This is the same as these, 1.47 squared over 50 plus 2.31 squared over 50. When you do that, you end up with the following quantity. This becomes a negative 0.36. I have plus or minus, this whole quantity becomes 0.7589, giving me this interval, negative 1.1189 up to a positive 0.3984. Notice the difference could be negative. The difference could be positive. Could be either one, which means the first mean could be bigger, or possibly the second mean could be bigger. We would not be sure. This interval, because it goes from negative to positive, is saying the same thing here, that we have to continue to assume there's no difference in those means. They basically support each other. I'm going to do one more example here today. The good news for today is we will have no assignment. We're going to spend 2 days on this section 10.1. But here's another example. An Ohio University, and again, I should have cut the top off. wishes to demonstrate that car ownership is detrimental to academic achievement. It means if you own a car, you're likely to get worse grades. Believe it or not, this particular test is run in multiple universities or colleges. Frequently, it does actually show that car ownership or having access to a car while you're living on campus is not good for your academic achievement. Frequently, it shows that if you have access to a car, own your own car, or can drive someone else's, you tend to leave campus more often to go uptown to wherever, movie or whatever other kind of entertainment, and you spend less time studying and staying focused on your grades. Hence, it's detrimental to your academic achievement. There are colleges, by the way, that actually restrict freshmen from having a car on campus because they want them to stay on campus studying their academics. And you thought Northwestern was bad. Wow, we at least let you have a car if you want. I'm just kidding. Okay, let's see how it turns out for this Ohio university. We first want to find a 95% confidence interval. Again, I'm going to do that down over here on the lower side. 95% confidence interval. It's going to be, in this case, x1 bar minus x2 bar. Same formula, plus or minus our z-score times that same adjusted standard deviation. So in our case, what is the first mean? Well, the first mean in this case did not have a car. It was 2.68 minus the second one. These are the people that did have cars, 2.55. It is lower for the ones that did have cars, but is it enough lower? Does that give us mathematical evidence? 95% is 1.96. The first standard deviation was 0.7 over that sample size, which was 100. Second one was 0.6 squared over 100. Turns out this ends up being a negative 0.0507 up to a positive 0.3107. Again, notice going from negative to positive. So for this university, we don't have evidence to indicate that owning a car is detrimental, all right? If we had to run the hypothesis test, I'll go a little faster now. Hopefully by now you're pretty accustomed to it. Got to first define what mu1 is and what mu2 is. Both of them are means. Mu1 is the first one listed. The first one listed was the ones that did not have a car. So I'm going to go mean GPA, no car. Mean GPA with car. This time, here's where the part gets tricky again. The reason this one is tricky, this is a common place to make an error now. We're trying to see if there's strong evidence that a car is detrimental. Detrimental means that if you have the car, you get a lower GPA. GPA with a car would be lower than a GPA without a car. This one would be lower, the second one. The second one would be a smaller number. I'm trying to show that it's detrimental. I'm trying to show that the second one is smaller. If the second one is smaller than the first, the difference would be greater than 0. That is crucial right there, greater than 0, that you can make that determination. We're trying to show that it's detrimental. With the car gives you a lower GPA is what we're trying to show. Trying to show the second one is lower than the first. This one would indicate no difference, equal to 0. Make sure that you can come up with that. Rerun this multiple times if you have to get where I'm getting that from. That is a tough part for a lot of students. Okay, well, continuing on here. Strong evidence is like saying alpha is 0.05. My sample sizes, both of them were 100. N1 equals N2, which equals 100. Therefore, I'm using a z-stat. They were both over 30. If either one of them is not, I have to use a t-statistic, which we're going to cover in our next video. You think the formulas are nasty here, they get worse with t's. All right. Last time I think I did a p-value. So this time let's go with a rejection region. It's a single-tailed test. Again, you don't need this drawing, but I'm going to put it in there. We're testing if it gets to be a big enough positive number. So this time, my rejection region is on the positive side. It's this one right over here. I'm putting all 5% in that rejection region. That gives me 1.645 for that line in the sand as we talk about it. If I go over that, if I get to be greater than that, so my z would have to be greater than 1.645. That's my rejection region. Step number 3. My formula is again x1 bar minus x2 bar minus our hypothesized difference divided by this same standard deviation, and now goes in the denominator. Standard deviation of the first sample squared over the size of the first sample. Standard deviation of the second sample squared over the size of the second one. So I'm going to substitute in each of those. The GPA of the first one was 2.68 minus the GPA of the second one, which was 2.55, minus the hypothesized difference, which is 0, divided by 0.7 squared over 100 plus 0.6 squared over 100. Turns out that that z-score turns out to be 1.41. 1.4 did not go over my line. 1.4 is about in there. It is insufficient evidence for me to doubt the null. So my conclusion, you don't mind, I'm not going to write it here, I'm just going to say it. My step 4 would have been z equal to 1.41 is insufficient evidence to reject our null, and thus we continue to assume there is no difference between the GPA of those who did not have a car versus the GPA of those who did have a car. It supported what our confidence interval had as well. In our next lecture, I'm going to start off with the review of one where I'm not testing against 0. What I mean by that This past one, I tested against 0 because I looked at my difference to see if it was 0 or greater than 0. We'll be starting off our problem tomorrow where this 0 is not the number 0. It's something else instead. But because of time, we're going to stop for today. No assignment for today, but I will see you on Wednesday, and we'll be finishing up section 10.1, and we will give an assignment at that point. All right? Have a good rest of your day.